Okay, welcome to the first lecture of rigid dynamics. Okay, I didn't bother explaining this, so I'll just explain now. The history of this is that, okay, so we first skimmed over the wave function, which is, if I recall, we first skimmed over the wave function in Femboyology, which is minus h bar squared of 2m times the nabla squared, or the second Laplacian operator, of our wave function, or, we're going to use states here, but okay, I'll just write both of them. So our wave function plus some weight function applied on our wave function is equal to the energy times the wave function. Or if we reduce it, it is just the minus h bar squared over 2m of the time derivative of our wave function over dt is equal to e times the wave function. Now another form of this equation is the time-independent Schrodinger equation. So this is the Schrodinger equation, but another form of it is the time-independent one. E here is our energy operator, and it is in the form of IH times the time derivative of this. So E is equal to I h bar, or just h, just Planck's constant. It's actually h bar, the reduced Planck's constant. So recall that the reduced Planck's constant h is equal to h, which is actual Planck's constant, over 2 pi, or 2 pi, sorry, 2 pi. That's the reduced Planck's constant, and we're going to need that throughout all of the studies, especially when the parts concerning quantum mechanics, and times the time derivative, so dt with respect to t. So that's one. So if we want to compactify the notation, if we want to make the notation more compact, we're going to say that the Schrödinger equation is equal to minus h bar squared over 2m times the time derivative plus the spatial derivative with respect to x plus the spatial derivative with respect to y plus the spatial derivative with respect to z times applied on the wave function plus the weight function applied on the wave function. The weight function, by the way, is a function of x and t. Okay, is equal to the energy times the wave function, or applied on the wave function. And then, if we only consider one-dimensional traveling of the particle, or if we're only concerned with measuring the particle with respect to one dimension or 2 dimensions, so we're only moving, one dimension only. So we're moving back and forth only in one axis. Then this reduces to h bar squared over 2m times the spatial derivative, I believe. If I just write it here properly. Yes, the second spatial derivative with respect to x of your wave function is equal to the energy times the wave function. And recall that I wrote a while ago that the energy operator is I, h bar, derivative with respect to time. And so this becomes h bar squared over 2m times the spatial derivative, or the second spatial derivative of the wave function is equal to I h bar, the temporal derivative, or just the derivative with respect to x of our wave function. And whatever function that solves this Schrödinger equation, or this equation, or any of these equations, is what is called a wave function. So recall that this is Schrodinger's equation. Schrodinger's. Also notice that it's actually better when we're talking about light quanta, especially when we're talking about light quanta or something that involves like waves and stuff. Like say we want to model a photon, or if we want to model a gender fluid person, it'd be best to describe the wave function with respect to a sort of state. So we associate a state with our given person or our given system, and then we plug into the wave function and see if it solves the wave function. I mean, not the wave function, but rather the Schrödinger equation. So recall, let's go right up here. Minus h bar over 2m spatial derivative with respect to x. The wave function is equal to e applied on the wave function. Okay, so let's shorten that out. And you notice that this is actually the Hermitian operator, the Hamiltonian operator, h hat, and that's equal to he. So now, our wave function here becomes an eigenfunction. So these two are eigenfunctions. They have to be the same function to satisfy this equation. And then we have our eigenoperators, h bar and e bar. So our energy here is our lambda. H bar here is our permission matrix. And psi is our eigenvector, if we think about this in respect with linear algebra. So now, I mean, come to think of it, we're close now to expressing this in terms of a matrix, some matrix, some matrix, and then some vector, whatever the vector is, with some lambda times the vector. We're close to that. But we're going to need to use some linear algebra, of course. Let's first talk about basis. So if we use Femboy theory here, we could use the O cross P interval and the standard topology that we used on it, and use that. Or maybe let's use position theory in aiding for our mathematics here. So let's use the O cross P interval, or the O cross P space with its topology. Let's use that. Now, let's pick a basis vector, two basis vectors, of course, that will serve as, the basis for our system and what we're going to use throughout this, this discussion. So let's pick I hat to be 1, 0, just 1, 0. And the reason why they're unit vectors is because they're supposed to have a measurement of only 1 in their respective direction. And our j hat is the opposite, 0 and 1. Let's use this for our basis. Okay, so now notice we can describe our wave function with respect to this. So now we can call this our wave function to be equal to, of course, I times the wave function, or actually the wave state. Or now let's change the notation to big psi to small psi. And you'll notice that it is now as close as we can be to a smaller, or to the conventional or the modern notation for this kind of thing. So small psi equals big psi times I hat plus big psi times j hat. And so now it becomes a vector function. And so this describes sort of wave-like phenomena. And then you can think of it as vectors going up and down continuously in sequence. Of course, if we think of it as like an electromagnetic field, it goes something like this, and then you notice that it's both in the x and y direction and stuff like that. And then, of course, yeah. And, yep, that's what. So first in the up direction and in the down direction. Now, if our wave function is only concerned with if our wave function is only concerned with one-dimensional, I guess, curves here, and not curves with another curve in the third spatial dimension, then one of these is going to be 0. One of this is going to be 0. Either I hat or j hat are going to be 0. 0 value. Because of course we don't have basis for that dimension because our particle is not traveling in that dimension and only in this one dimension, which is I hat or j hat. Okay, so now we have this, but actually let's generalize it further and not just say that it's just psi, but let's call it alpha and beta. Wherein alpha and beta are complex valued functions. So they're part of C. Okay, but the thing is, we're one step closer to using the actual notation used in quantum mechanics. Instead of I hat and j hat, let's use these two things called ket vectors. So you notice this is already a ket here. This is a ket vector. Now, let's say that this psi is equal to, of course, alpha times the spin side state plus beta times the spin up state. So now we're talking about states, and of course, if we plot these things here, we get ourselves a state or a certain person, right? And yeah, these vectors express these things in terms of a person. And you notice that when we do construct a wave function for a person, right? It's some amplitude, something like this, wherein it tells us the likelihood that someone is here, or their attribute or the characteristic is here, or this characteristic. And so yeah, when we take the norm of the wave function, we actually get the probabilities, because the wave function itself is not the actual function that gives us the probabilities, but rather when we take its norm, that's when we get it. So the norm is some operator that takes our function space and then it maps it out to a separate function space, wherein our first function space is the space wherein we have our generalized wave function, and then of course the codomain or the image of our wave function belongs inside another set which gives us the actual probabilities of the thing. So so this norm, which is denoted by these two absolute value symbols, maps our current space O cross B onto some normed space. Okay, and so the actual norm of your wave function, let's use just the regular, the function itself, not the state just yet. It's actually the same thing. And that's equal to just the wave function multiplied by its conjugate. And the conjugate is just the opposite of it. So if our wave function is, of course, alpha I hat plus beta j hat, then its conjugate is just alpha I hat, or actually, since we're not using the states here, this isn't a state. State function, let's use I. We have to use I, just I, wherein I is, of course, equal to the square root of -1. Because, of course, once this is just one-dimensional for the time being, this is just regular R space. Once we add I here, we have a second dimension now. So we have the real axis, and then now we have an imaginary axis, where it's multiples of I, and so we get ourselves a complex number. Because that's what we need here. We need complex numbers to better describe the probabilities and stuff. Because the wave function is not a real valued function, but a complex valued function, actually. I mean, you can say in the classical sense that it is a real valued function. In fact, when we do take the probabilities are real valued. We can't have complex number probabilities. We can't have I% or 0.0i. We can't have that. So really, when we do take the norm of this, or when we multiply it by the norm, we end up actually normalizing the space, and that's another reason why we call it normalizing, because we turn the complex valued wave function into a real valued output, right? Which is the actual probabilities of our given person or particle being at a certain position or time. So now our, if we express this in terms of A alpha plus I beta, where alpha and beta are real numbers, of course, or if you want, they could be, alpha and beta can be elements of our F space from femboy theory. Recall, we can take two femboys here, and then we can spit out some complex number. So the conjugate now of our wave number, whatever, is alpha minus I beta. So the conjugate is just us switching the signs here, or the complex conjugate of this. Okay, so the norm now, if we let this be, of course, this over here, then you notice that the norm of this, or yeah, the norm of psi, the norm of psi is equal to A, or alpha, plus I beta, times alpha plus, minus I beta. And then just use multiplication. So this is alpha squared plus I squared beta squared. And so I squared now is equal to the square root of the square of the square root of minus 1, which is minus 1. So this flips sign. Actually no, this is minus. Because b squared here, this term here is minus. So alpha squared, and since this is minus 1 now, it flips sign, plus beta squared. And then you notice, it's neither negative nor complex valued. So now, this proves to us, or this tells us that indeed our probabilities will become real valued functions, or real valued outputs, instead of complex value. And it's actually normal to normalize, or to take the norm of functions, or wave functions here in quantum mechanics. In fact, that's always done. We normalize wave functions because we don't want to end up with complex valued probabilities when it comes to our certain person, or characteristics of a person, or a particle, when we treat a person like a particle. So we don't want these kind of things. So a squared plus beta squared, or alpha plus beta squared, gives us real valued outputs. So likewise, when we take the norm of our state function, or state vector, when we take the norm of our state vector, which is originally complex valued, like I suppose the psi, small psi, when we take its complex conjugate, I believe it's denoted like this. We use a bra vector. So the bra vector is just the opposite of the ket vector. It's just the ket vector in a different direction. And if I remember correctly, the bra vector gives us a column vector, while the ket vector gives us a row vector. So something like, let's say alpha gives us a row vector, while this alpha gives us a column vector. And so taking these two, and then taking their square, gives us the probability amplitude. Actually, this is not just the norm, but we also sometimes take the norm squared. And this is to ensure that the... Wait, what are you doing? Is he sounding? Again, really sorry. I wish I could lock the door, but that always happens. I know it's sort of an offense, but there's nothing else I can do about that. So, if I'm not going to get sidetracked further, right. God, I got lost. Okay. So, oh my God. Okay. So one example of the wave function that solves the Schrödinger equation that people frequently use, especially when it comes to light quanta, is the function e to the minus I times some value. So okay, let's say we have a gender fluid person. So in our O cross P interval, their gender identity fluctuates between male and female in some time interval, and we want to quantify that, or we want to construct a wave function for it. Okay. So okay. So we have our O, and then we have, or actually this is time. Sorry, this is T. And this is R O. And then it fluctuates back and forth between M and F. Let's say we want to construct a wave function here. So of course, we can think of each snippet of this function as a bunch of vectors going up and down in sequence. And so of course, we can construct a wave function from that, or a state vector type wave function. So what is our psi? Okay, so think about it. Okay, let's have our Schrödinger equation. Let's have our Schrödinger equation. And so this is minus h bar squared equal to 2m. Oh, actually h bar squared, sorry. I just wrote h bar a while ago. It's actually h bar squared times the second derivative. Or let's use the time independent Schrödinger equation. So time is not dependent, or the probability is not dependent on time. So let's just use dx of psi is equal to I h bar dt psi. Okay. So what is psi? What function satisfies this differential equation? Well, we can always resort to, of course, separating the differential equations. This is in fact a separable differential equation. And then, of course, we can find functions that we can integrate, and then, of course, arrive with this output, or something that solves this equation. Because the primary goal, when we have the Schrödinger equation here, and when we want to construct a wave function, is that we find a function that indeed satisfies this wave function, or this Schrödinger equation, that also satisfies certain boundary conditions. So let's say that at time equals pi, or this is pi here, this intercept here, or the x-intercept is pi, 2 pi, 3 pi, 4 pi. Let's say at pi over 2, the person identifies as male. So our t value is pi over 2. So at t equals 2, or pi over 2, O is equal to m. Now it can be thought of as a number. You can think of it as I, and then this is minus I. Let's say that. Okay. Let m, or the male state, male identity, be I, and let f equals minus I. So we can just simplify this. I minus I. And then at t equals pi over 2, O is I. Okay. So what wave function satisfies these boundary conditions? Of course, since we noticed that this function here is a wave-like pattern, of course, we have something that is akin to a trigonometric function, like sine or cosine. Oh dear. Okay. No notes for this one. Okay. Sine or cosine satisfies this equation, of course, because notice that they are also waves. They model waves, and so that's a reason why we use sine cosine. And notice that if we take the Wronskian of these two functions, if if we take the Wronskian of sine and cosine, which is just basically the determinant of a matrix containing certain high order derivatives of the two, then, and if it gives us a zero or a non-zero answer, then the two are linearly dependent in that when we do add them together, their sum becomes a solution to our problem. And in fact, that is true that when we do add these two, or when we do start to construct our wave function from these two, they do give us this type of solution, or they do give us a solution. So, okay, cosine and sine works for this. So actually, when we do construct psi, or when we find psi, we have to find alpha and beta, to be precise. We have to find these two. What is alpha and beta? So let's say that alpha is sine. Sine of t, because we have a function of t. So O is a function of t times the up state plus b times the, okay, let's say b is cosine, or let's switch this, let's make it interesting, say this is cosine t and this is sine t. Oh, sorry. This one, sine t. Sine t. And then the spin side state. Okay. So there it is. This practically solves it, but let's introduce some other stuff like phases. So the phase here is I. So well, I has to be over here because I is the amplitude. I cosine of t equal plus I sine t times the spin side state. Because this is the amplitude, A has to be put here so that when we multiply these guys, they give us the same, a height as here, and so it would satisfy our condition. And if we extend this a bit over here, notice that it is not symmetrical. It is not symmetrical with respect to the origin. So, in fact, what I was saying was a trick, because one of these sus functions do not solve the equation, because when we notice here, with our example, our sample problem, it is not symmetric. So one of these guys are not the solution. Because one of them starts at I. At t equals 0, some of them starts at I. And so it wouldn't be really that. In fact, our output would be I1, I over 2, once we get to pi over 2. We get somewhere over here, because it shifted for it to be symmetric. Now notice that cosine is an odd function, which means that it is symmetric with respect to the origin. So therefore, sine here cannot be the equation that cannot be the solution to this. And in fact, notice that sine here, it eliminates cosine, because cosine tells us that it's also in a different direction. So now it's going there, and then sine here tells us it's going here, or in this direction. So we eliminated a potential dimensional error, because we're only working in 2 dimensions here, not 3 dimensions. So our new answer is I sine t times our spin side state. Okay. Last thing to do before we wrap up the lecture is notice that the phase of this, the phase is pi. So now, this is I sine of, we have to multiply t by the phase, or the period, so that we get the same period here. So that at pi, at t equals pi, our identity is 0 or none of them. So now it becomes. Good morning, miss. Sorry.
Sorry,
No, it has. I'm sorry if it extended this long, miss. I didn't expect it to be this long. Okay. So the final answer that solves our Schrödinger equation for this certain person is I sine pi t times the spin side state. And actually, that's it. That's all the time I have for today.